in a few seconds. Huh. Okay, now we're ready to go. Boom. I'm pressing the button. Huh. Alright. Hello everybody and welcome to the stream. I really should have prepared more for this stream. Hold on a second. Let me go ahead and shrink my tab down really small. Real quick. And then resize it. Also really quick. Because I need to make sure everything is in check so we can be good to go for this stream. And make everything all nice. That's probably going to be pretty wacky. There we go. Let's make that a much better size. I need to remind myself, like I need to leave a note tomorrow, so that way when I go to record, that the screen is kind of gonna be whack. Okay, let's go ahead and do that real quick as well. Fix screen. Okay. Yeah, I should have prepared more. Okay, we're ready to go. And now I can kind of see the chat when I do this, and I can't really tell who's in and who's not, but that's fine. Alright, so I've begun working on a new project, and I have finished my previous project, and I'm going to go ahead and talk about a few things about the new project and my goals with this one. So, let's actually go look at my goals from the previous one, and then we can have a reference point of where we're starting off and what we have that we've actually got done. So, we'll start off with the very first computer I made. Control. We didn't have a control circuit. We had an ALU and we had memory, but that was good. And we also figured out a ton of stuff about what to and what not to do, and all kinds of crazy stuff that was very important. So then in the next design, we got actual control circuitry, a display, and this I'll show all this off in a video tomorrow, probably. But anyway, we went through several different designs. Initially, I thought it was going to look like this, with registers and all kinds of things here. But in the end, it ended up looking like this. Big display, tons of buses on top. Everything is stacked instead of spread out like the other one. The other one's like a big piece of butter. It's spread out. This one is stacked. It's very good. And what were my goals for this one? Well, I have it all written down here. So more compact, that's one of the goals. More functions, always good. A GUI, did not do that one. We were not able to do that one. And just generally being better, yeah, that's true. Then my new goals from there are, well, new things I learned. Base 4, we have that. That's the display. How to convert to that. ROM and RAM, learned what those are and how to use them. So we've learned a bit. And I started working on my next things as well. Anyway, let's go ahead and talk about some different other things that are also important to this thing. And I'll talk about conversion, because I did discuss this in my video that I'm going to upload tomorrow. But I didn't actually talk about it. I didn't have time to talk about it and all how cool this is. But basically, in pretty much any logic system, you can convert to the other logic systems and number systems. So, for example, let's go ahead and take 4 binary inputs, turn them into a hex input, like this machine is doing here. We could actually use a red coder for this and turn that into one of these being active at a time, so it tells us what it is. And, you know, when one of these is active, we could have it perform a certain task. But, okay, well, anyway, we'll be done with that. So, basically, one of the things is that you just put hoppers and you use comparators on subtract mode, and you can take, let me go and demonstrate, a binary input and turn it into a hex input. This isn't really hex. I don't think this is hex. This is kind of like base 15. It's not really hex. It's kind of missing a number. But I guess in a hex, when you hit what is it called? When you hit 15, the next number is going to be 16, so you carry over. So it is technically hex. That's right. Okay. Anyway, I really should do full videos about these number systems, because they're very nice. I like numbers. Okay. So, this one has a strength of 1. So if we put that in there, it should only activate the first repeater. Boom. If we put this one in here, because this one is 2, basically, if we do this one, it should have a strength of 2, because that's, it's 2. I just got a notification about myself being live. How? This happens every stream. Anyway, I'm gonna go ahead and explain more. So, if that's 2, then 1 plus 2 equals 3. And it counts that out in hex. This is also how analog circuitry works, and analog circuitry is gonna be, that's quite interesting, because that's got some potential for computer stuff, and I am interested in building analog computers at some point. So, what is, okay, how do we get to 4 then? Well, you just activate that one. That's a 4 in binary. So, yeah, that's how we convert to hex. And if you wanted to represent this using numbers and letters, you go from the numbers 1 to 9, and then I think it's A through F. And in this case, technically, I think we carry over once we get to that point. I don't have a system for hex addition yet, but I think we could do that at some point. But not right now. That's not important. So, basically, if you can do hex, then what other things can you do? You can also do, in theory, you could do a 6, a 6 system, or an 8 system. You could do octal. So 1, 2, 3, 4, 1, 2, 3, 4. That's octal. Then you could do, if you don't want to do octal, maybe you want to do 6, which this is called hexamal, or there's another one for it, but I won't say that. Basically, this is base 6. There's also base 4, which is what we used over at the digital displays that I showed off, or am gonna show off in the future video. There's also base 3, and this one is the most interesting to me, but I will not talk about it. Basically, we're only gonna talk about the even ones right now. And also, there's our number system, which is base 10, so that'd be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you may be wondering, why exactly would we only want to use, certain systems for these? Well, like, why can't we just use base 10 for 4 inputs? Because, well, if you take 4 binary inputs, that actually can represent the number 16. And that actually is not 10. So it's, basically you'd end up with an overflow to where, you can't represent the numbers. However, there is a solution to that, and the solution would be to take, for example, in base 4, we can just take 2 binary inputs, because 2 binary inputs can only add up to 4. So let me go ahead and show you all a truth table for this. We'll use, let's just make, we'll make this thing with a bunch of expensive blocks. So, alright, let's go ahead and do this. So in binary, let's say we have a four-digit binary number here. This is a nibble, or like half a word, or half a byte. A word is 32 bits. But we'll not talk about words yet, because that's data storage kind of stuff. Anyway, this is what a whole, like, this is the chart I use usually, just to represent how the numbers look. Not really a truth table, but kind of helps with visualizing it. You'd also count binary on your fingers. I discovered that. But basically, the number 2 in binary is the middle finger. No other fingers. Okay, there we go. So, there's a pattern here, where once you hit this number, you end up with, basically it just repeats. And once it carries over, then it's kind of simple. Binary simple. But we'll talk more about these things, because there are certain things that are very important for me to talk about right now. But, hello. Alright, here we go. Okay, there we go. So that's what a binary table can look like. So in this case, we have 4 zeros. We have a 1. We have a 2. We have a 3. We have a... Okay, let's go ahead and represent these with signs, just to... I'm not sure why I'm talking about conversions, but we can talk about a lot of stuff today. So we have 0, 1, 2... Oh. And this is actually a BCD representation of binary, but because you can actually have just very large numbers, you can go up to, like, whatever number of bits you want. You can have as many bits as you want. Most computers go up to, like, I don't know. I have no clue. I don't do real computers, okay? 3, 4, 5, 6, 7, 8, this one is 9. Hold on, it's hard to find the numbers on my keyboard. So in normal numbers, as you can see, in base 10, you go up to 9, and then you carry over, and then you end up with 1, 0, which is 10. In binary, you can represent 16 numbers. In order for us to actually represent the number 10, we can only take... Well, we'd have to take 4 inputs, but those 4 inputs could add up to 16. So that's why base 10 conversion is quite difficult. So, you know, because we could end up with... we need 4 to represent the number 10. So we would need 2 panels, 2 7-segment displays to represent it, which is why it's easier to just use hex, because in hex, you can count up to, this one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Actually, no. Hold on, we stop at 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then it becomes A, B, C, D, E, F at the end. I counted wrong, so this one is 0, 1, 2, 3. It's simple, okay? Basically, we can represent 16 numbers using only a single character. There's also base 32 and base 64, but those aren't really, those are not really practical for this usage. And as you can see, this actually is quite a cool pattern. I really like it. It's like an inversion of itself. So once you pass the number, yeah, it is very choppy. Sorry about that. Okay. All right. So I'm gonna go ahead and let's begin talking about octal then. So octal, if we talk about octal, octal is pretty cool. Octal is able to represent 8, so theoretically we can take 2 inputs to represent a total of 8 numbers. So from here to here, this is octal. Hex can represent from here to here. This one is this one's 8, right? Or is this one 8? I think this one is 7. That one's 7. So this one's 8. So we can represent from 0 to 8 in octal, which is a problem though, because converting to octal isn't really practical, because you still end up with this, having 4, where you could end up with 16. So octal is not really something I can use for most systems. But I would really like to use octal for something. And you know, I have an obsession with using the most obscure numbering systems for all my projects. So we'll just put a mangrove log here, because this is basically not possible using a decoder, unless we do like some fancy stuff. Now let's talk about representing hexamol. Hexamol is different than hexadecimal. Hexamol represents up to 6, and theoretically this is that's 5, that's 6. So yes, hexamol is practical. We can do hexamol. We can do that fine. What about, how about base 4? Well, base 4, we can do base 4 as well. So we can represent that, I think. Yeah, base 4 is perfectly fine. So there's a total of 3 systems I'm gonna just say are fine, but there's one problem with hexamol over here. As you can see, you can also represent the number 7 in 3 bits, so that is a no-go. Except, unless we carry over. Maybe it is possible to do octal. Maybe it is. I mean, I don't know. This is questionable. I don't really know if I can actually set up a system that does that. We're gonna talk about some other things at some point. So there we go. We have this is like our chart here. Okay, so the next one is well, base 2 would be the next even, so that's just binary, and that's, you know. So theoretically, we can represent this one using 2. This one we would need 3 to do, and we'd have to make sure that it's never 7. And on this one, we can use a total of 4 to do, but it's really, I don't think it's plausible because you can end up with all these big numbers. I mean, with hexamal, it's at least kind of acceptable because there's like, you know, a one number gap. So, yeah, there we go. That is number systems, and they're very interesting and useful. So over here on the computer over here, we're using a base 4 system to represent the displays. So, as you can see, this is a 1, which means that the 1 signal strength is on. So that means this one's on. And I've done it a bit backwards, but, yeah. And really, I messed this up. I should have, if I wanted to do this right, I should have represented these as, like, a BCD conversion, and then had it convert into 2. I think it's fine, because these actually convert into their places onto this thing. So, I mean, I don't think it'd really be necessary to do that. And, yeah. We're not going to run this, though. We're not going to run this. So, next thing we're going to talk about is... You know what? Let's talk about my system ideas for future systems that I'm going to be working on. And I'm going to reveal one of the big features about my next project. Okay, well, let's go ahead and get started with this. So this is like my little test area for certain circuits and systems and things. And, it's out of the way from all my other projects and computers and things that we're working on. Let's go ahead and begin creating a system for, you know, selecting a certain code. So my next computer is going to be able to read input data via a hopper system. So we're gonna have a so basically what I mean is that we're gonna be able to just you know. Hold on a second. Let me just think for a second. I need to set up item filters for these. I don't remember how to do that because I haven't played survival in a very long time. That's vanilla survival. I'm thinking it's just a redstone comparator output, and that tells us how to set them up. And I think it's just like you need to make them locked when they have a certain number of items in them. So it's like 5 stacks of items, and then so like I'm thinking it's like I'm trying to reinvent the wheel here. Okay. So we have this. That's gonna lock some hoppers, I think. If I remember correctly, it locks the hoppers over here. Is that right? Is this right? I don't remember how to do item sorters. I think this is... Hold on, let me look up an image. I need an image. Item sorter. Minecraft. I know it needs comparators. Oh no, my internet deep fried itself. This is great. I guarantee my internet crashed. My internet service providers are garbage, but that's fine. I don't have a problem with that. Okay, we'll just improvise this. We'll just say that the system needs to be like this. I'm pretty sure you'd put the torches beneath the system. And then we're not doing a red coder. We're not doing that. We're gonna just hook this in. I believe you can just read them through the blocks. So you can just take outputs from these guys and do like that. And that reads the item filters, I think, if I remember correctly. Then all we have to do is put something like this, redstone dust on top, and then shove repeaters in there. Man, this is just so messed up, this system here. Okay, let's go ahead and do this, and we end up with that. That's kind of not what I wanted. I think it has to be. You know, there's a reason that I didn't create these things, or I've never used these things, and it's because I never ever use them. So I never know how to actually make these things and have a functional... Oh wait, those are always going to be on because of the repeaters. That's not supposed to happen. hold on a second. If that's how that normally is, then theoretically we can just lock them through the bottom, and then definitely reinventing the wheel here, just doing it worse. Okay, then we need to take outputs from those and use them like this. I think that's how item sorters work. I don't even remember. It's been a while since I went to Redstone school, but hold on. Let me fix this up again. And that should be the item sorter. I think that's how they work. So now if I just put like a ton of these guys in here, that should always be off unless it gets another one. And then it toggles the system. No, it's just always going to be off. Hold on a second. Wait a second. Oh. Now I remember how they work. So they need to get to a certain signal strength to actually function. And turn those off and let them in. That's how these things work. You know, whoever made these is a genius. Whoever invented this, because it's not me, they are a genius. Okay. That's where the interesting part comes into play. I need two hoppers to do things and make it work. So, boom. And then I used to use this design on the Bedrock edition. I'm not sure if that's actually supposed to work on the Bedrock edition, but I'm pretty sure it did. And everybody says that Redstone is not very similar between versions, but I've never really had a problem going between the Bedrock edition version of Redstone and this version of Redstone. Even though I like this one better, because it has a bunch of better features. I mean, to be honest, being able to move chests around with Redstone is actually pretty cool, but I'm pretty sure that's the only cool part. Like, I don't like that pistons don't spit out their blocks. That's like that's the worst part of Bedrock. Alright, so that should be, and any other bugs. Which that should load this thing. Oh, it needs to be inverted, so it doesn't actually just throw all its junk into here. This one needs to be locked when... Oh, wait a second. No, I don't know. I don't know. I need the answer. Okay, well, let's go ahead and take a look at item sorter Minecraft. Oh, hold on, I have a phone. Maybe I can use a phone for my internet sorter. I'll just use my phone. I'll go get that in a second. I'll be back. It'll take me like 10 seconds. Do. My chat is disabled. Okay, that's fine. I can't really read it. So, short intermission because I can't figure out how these things work. Okay, now I just need to find where I put my phone. I always keep my phone in my bed because I only use it for my alarm clock. That's about it. And nobody ever calls me. Okay, here we go. We're gonna use a phone. Oh no, I put 7 numbers in. It takes only 4. This is the elevator music. So whenever I have the answer or need the answer to something, I usually just Google it. And then if I can't find a good answer that I like, or if I find the steps to solving the answer that I'm looking for, I'll just, try to invent the answer I'm looking for, if that makes sense, or discover it myself. Which usually learning the concept is the most important part. My phone is very slow because it only has 15 gigs of memory. Actually, let's talk about bytes for a second, because so if a byte represents 8 bits, right? Then a megabit is like, hold on. So a kilobit, no. A kilobit is like 10 bits, but a kilobit, I don't know. Maybe it's a decabit. I think I don't remember. I don't remember the metric system. Okay, hold on a second. Let's go. What am I looking for? I'm looking for item sorter. I got sidetracked. Sorter. Yes, tell me about item sorter Minecraft. This is good. Alright. Oh, I was very close. I was very, very, very close. This is how I did it, like, a few years ago. On Xbox 360 edition. And it was, like, terrible. And didn't actually work. Because it was just not an item sorter. It was just like a hopper with some fancy extra redstone bits. It wasn't actually an item sorter. Just item sorters actually are just like this. That's all you need for an item sorter. You just need this shape here, and you need. I'm thinking a second here. You need to shove repeaters into here. So I had that part right, and I had the comparator part right. I just didn't have the torch placement right. So this is the system we're using. An item sorter to read commands from, you know, an input. Which, this will allow us to have a database of different commands that can be inputted and then read by the machine. And we can use analog circuitry to do that. And this is the basic idea for my next system. So that way I don't actually have to put lines into the ROM. The ROM can just know what it's gonna do. So we'll go ahead and explain this thing. I mean, I don't need to explain this. There's videos out there. People will do a better job explaining redstone than I do. I'm just here to make cool things. Okay, so we need to set up a series of chests here. Alright, we need, not trap chests, but we need some chests. We need, like, where do they put those? Do they put them in decorations or something? I don't know. I usually just use JEI, but, I'm using vanilla. Because I mean, I don't really want to install another modded installation for 1.19. I've got 1.16 as a modded installation. I got, 1.12... 1.7.10. I don't need a 4th installation. Okay, here we go. So this should be an item sorter. Well, let's just shove a bunch of redstone lamps in there. And let's say we want the input to be a we'll use pieces of paper here for this. And then we'll use an anvil. So we can just use the anvil to make the system write a certain letter, because we can just, let's say, run. This is a run command. And now we have 64 of it. There we go. This isn't too far how computers would have worked ages ago. They would have just taken sheets of paper and shoved them in there. No, I'm joking. They use special things. They used big rollers, which is how I got the idea for the roller reader. So we need more papers. Run. We'll have stop. And then we'll also have, I guess we could have, I don't know. Maybe we want a conversion system, so maybe we want it to use the hex converters? No. We could just have it doing all the conversions at once. We could have it do that by default. Let's just say we want this to, write. I think that's a thing that computers typically do. So they write, run, stop, and paper. Let's go ahead and make one last one. We'll call this one delete. I mean, that's not a function that I had. It was just read, write, and then unwrite. So basically, to unwrite something, you just hit the button when there's no power input going in, and that's how you would delete things. Okay, so we'll say this one is gonna be. Let's make sure we have a ton of these. This one is gonna be run. We'll put the run into there. Boom. So now if we shove a run into here, it should just go into here. Go into this chest, but it went all the way to the end here. That's because this system is a failure. It's miserable. It's a... Wait a second. What? What? What on earth? Did it not work? Did it work? Oh, it did not work. Now that's quite interesting. That's not what I was expecting to happen. Let's try this again. So I should put, if I put run into here, if I put like oh, wait a second. It's not actually reading the output from these, is it? Or maybe it is. Maybe I have the item sorter all wrong. Again. Maybe it's actually supposed to be like this. But I don't think that would work. So we'll just put run in there. So put 2 more pieces of run. Maybe one of them will make it in. Never mind. Let me look at the blueprint again. I'm pretty sure at this point you all get what I mean, but I just want to make it happen so that way it looks... Oh, that's the problem. Alright. So they actually used 2 hoppers in these. And I just used 1. And then had to go across. That's why it wasn't working. But item sorters could be the most important thing for this system. Okay, we need, so this one doesn't actually save the stuff. This one saves the stuff, but, put 1 there. As you can see, it's trying to put that in there. But if we put enough in here, then that should, work. You know, I'm done. Okay, basically, you all get what I mean. I'm gonna use item sorters to make things happen. And, let's move on. Let's move on from that. It's just like this system. It's simple, but I have to make it look extra complicated because who knows. Okay. So let's go ahead and begin working on the next thing. So typically, when I'm building a computer, I start off by building the logic unit, the arithmetic logic unit, over here, and well, my goal for this one is to have words. And you may be wondering, what exactly is words to a computer? Is it like English? Well, no, it's just binary characters, or sets of binary, you know. So for each word, this computer will use, instead of using 32 of these bits for a word, it's going to be using 4 for a word. Because I'm not building a massive processor to determine what each thing is. If that makes any sense. Plus, it'll be faster if we can assign certain things to certain other things. So, I saw that a bunch of college papers about this thing and how they break it up. Let's go ahead and begin breaking up what I want the words to do. So you need to know what the word is gonna do. So we'll just, maybe not. Let me think. Maybe we should start from the bottom and start from each individual bit. Well, actually, let's just make a big abstraction of this. So this word will represent, I don't know. And then this word will represent, hold on, I actually do have it pulled up. I could just look and see what it is. Alright, so we need bit fields, opcodes, operands, control bits, and all that stuff. So, okay, I'll read this for y'all. Every machine instruction becomes a binary number stored in instruction memory. The binary number is separated into chunks or fields, which is what we're doing over here. I've separated this into a total of, well, actually, we need 6, because I do have a 6 chunk that we can use. Let's just use some crimson blanks because they're there, and pink is a very nice color, if I'm being honest. Doot, 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 doot. So we're gonna do words. Basically, so they've broken it down to where it's chunks now, and okay, that's where we left off. So they contain the information about the instruction, because you can't just put an instruction in there without knowing what you're gonna do with it. So next thing is the field uniquely identifying the instruction as an add, subtract, or multiply, a move, a shift, etc. This is called the opcode. So in their system, they've set up the first one as an opcode. So that's what we'll do for ours. This will be the opcode. That will tell it whether it's going to add, subtract, multiply, or divide, or whatever it's going to do. So that will tell us what operation we're doing. The next one. So we have the fields identify. Okay, actually, is that? Yeah. The opcode can be located anywhere within the instruction binary number, but it is often found at the most significant end of the number, or the least significant end. And basically what that is saying is the most significant end, or the least significant end, is basically this number is greater than the number that's all the way down here. So this is a 1, whereas this is like a ton of 1s over here. If you convert it to decimal. I'm not converting this to decimal. This is a lot of numbers. Okay, so we've got that clear. All right, let's get to the next part. So it can either be at the front or the back, or in this case, I will always put the opcode at the front because it will just make things simpler. The fields identifying the locations of data are called operands. That may not make sense, but I'll make it make sense. So what I think that means is that there are certain codes that will tell us where we find the other codes, which I don't think is necessary. I think that is, I don't know. I don't really know that you actually need to know where the codes are. You just need to have them in a certain position by default, and that's what we're going to be using. We're just going to be converting everything into BCD in order to get it down to this, and BCD is 4 bits. It's a whole binary number represented in 4 bits only. So in this case, we're representing 24 bits, but in 4-bit chunks, and that's a very simple way of doing it. You could break it into 8 bits. You could break it into 6 bits. In this case, they've broken it into, well, their opcode is like 6 bits. They have another one that's 5 bits. They have another one that's also 5 bits. The destination is 5 bits. And the other one's 5 bits. But the function is a total of 6 bits. So the opcode and the function are both 6 bits. Which makes things simple. Huh. Okay. I'm not going to talk about that. Why that makes things simple. But, I mean, if the number... If the opcode can be found at the very first significant number, or the most significant number, or the least significant number, then it would make sense that the 2 chunks for those would be equal, and that's just, so. Alright, finally, control bits give information about the instruction to the CPU. For example, a control bit might command the CPU to capture the ALU result flag, which a flag just tells things what to do. The ALU is the arithmetic logic unit. The CPU is the central processing unit, which is, I mean, I think the CPU, I think that's just the whole thing. But I don't know. I mean, for most of the abstractions, I understand that I think that the CPU composes an ALU and a bunch of other things as well. But I don't think that, according to this article, that's not how that works. Okay. The fields form the entire binary number stored in the instruction memory as voltages. Well, we're not using voltages. We are not using that. We are using redstone. So it's either going to be an on or off, not voltage. I mean, we could do analog. We could do signal strength, but that doesn't matter. Okay. So this will be our opcode. He'll tell everything what to do. So I'm going to say that one. Let's just do a chart here. We'll do a chart. Make it simple. We'll do crimson and that equals addition. We'll just put a plus here. Wait, no, I don't know. How do I represent this really easily? We'll just say that addition will represent addition with like what color would you associate with addition? It's really easy, right? So I would say, I don't know. What is an easy color? You know what? Let's not even focus on this. Basically, I've just gone over everything that we need to know. So this will tell us what we're doing. This will tell us, I don't know. This will tell us, I don't know what this one will tell us. This one will tell us our destination. So this one is our destination of register. We should have a total of 16 registers because there's a total of 16 combinations there. Then over here, this one will be, I mean, I guess this is a number. And then this is also a number, I guess. And then we don't know what to do with those other two. Maybe I have too many bits here. Okay, well, we're working with 24 bits. This is a weird computer, but this is fine. And time to get to the worst part of everything. I really hate building these things because you have to build these massive repeated circuits over and over again. That's like the worst part of it. But once we get done with this, we get to start on the other worst part, which is just building massive lines of redstone dust. It takes a very long time, but I am very excited to get there. So, what operations am I going to be able to do with this new computer? I mean, a lot of computers, they do bit shifts and things. I mean, I'm not really too sure yet. And I think we need to, I first need to learn how to do those things, because I've only just recently learned how to subtract binary numbers. And I still haven't finished learning. I'm still watching that video about it. But I'm pretty sure from like most of the summary of that, you just kind of shift the bits and then add a bit. I don't know. That's probably wrong. Because I haven't done it yet, so I don't know how it works. Once I do something, I automatically just know how to do it. Again and again and again. But it doesn't really matter. Let me check and see if all these XOR gates are done. Okay, they're done. So yeah, all we have to do is like just this line of XOR gates, thankfully. So we don't have to worry too much about complexity, because we're just going to repeat this same pattern over and over again, and then shove repeaters and things into it. We'll just start off with the basic pattern for this gate. Now, there is one problem with this logic unit, as you all may be able to tell. We are working with a large number of bits, and the larger the number of bits, the slower this will. In order for this thing to fully add, it will take a very long time. But at least we're not working with 200 bits here. I would like to make a 200-bit computer at some point, but I just need employees to work with me. I don't have employees, and I don't have money, so I can't pay people. Pattern over and over again. And then I'm gonna invent a subtraction system. I'm literally gonna brainstorm it up on the spot, just because I can. I know I can do it. Working with numbers isn't very difficult. You just have to understand how to use logic gates in combination to perform a certain task, or how to perform, or well, how to do things in different ways. Because there's tons of ways to do math. And computers use innovative ways to do math. And sometimes those ways may seem a little complicated because we're not using 1 through 10 as our numbers. We're using, like, I don't know, just ones and zeros to represent 1 through 10. So it's a little bit different. But well, I'm pretty sure now that I understand the once I learned this, I could just do anything from here. Like, all you need is addition to do multiplication, right? Because addition, well, multiplication is just adding the same number, technically. It's kind of like that. It's kind of like adding the same number together multiple times. So you would need a system that tells it how many... Hold on, let me write this down. I need, like, a piece of paper. Well, actually, I do have a ton of pieces of paper next to me. Hold on. Let me just write this on the back of the work. Good. Okay, so here we go. Now I can never throw this paper plate away. So, first things first. In order to multiply, we need to... Because multiplication is basically just us adding 2... Like, let's say we have 2 times 2, right? That's just us adding 2 plus 2. And then if we have 3 times 3, that's just us adding 3 to itself 3 times. So 3 times... Well, it's 3 plus 3 plus 3. So you need a system that tells it what number to add and how many times to add it. If that makes any sense. And I like to write things down on paper, even though I'm just doing it all in Minecraft. It just seems more official to do it on paper. I also have a circuit modeling software that I haven't used yet, because I didn't need to. I honestly don't think it's easy to use a circuit modeling software when you don't understand what half the logic gates actually look like in their symbol form. I mean, I know what OR gates look like, but yeah, I know what an OR gate in Minecraft looks like more than I know what an OR gate on a paper looks like. So I don't use the software to represent what I'm doing. I just draw out what I'm thinking on paper. Even though I could probably simulate it better using the actual thing instead of just trying to simulate it in my head. It's a lot to process. Because I was working on a trit system, which is going to be one of my future projects. I really just want to use an odd number of bits, but actually it's called trits. If you're going to be, if you're going to use 3 inputs, it's called trinary, or ternary, technically. And I've talked about this before, but I'm just obsessed with it because it's just so obscure and so unique. I mean, it allows for much faster computing, but it's just so specialized and stuff. And really interesting to me. Just super interesting. Not sure why. Alright, I'm going to go ahead and... once I get this done, I'm going to go ahead and walk you all through what this is going to do. Because this may look a lot confusing, because this is just a bunch of logic gates slapped together to perform a task. And I've learned things between building my last computer and starting this one. We failed miserably. We needed this carryout, and we still had an odd number because we didn't have this carryout. This carryout is the most important thing I have ever learned about, and so is the carry in. So it's still even, but the carryout is important. So I had over here a logic gate for this system, but I realized that we just need a carryout because this represents 1, and if we're gonna have all these be active and then have this one on, then yeah. So there we go. And I'm really not too sure why it'd be necessary to have such a big adder. I'm not too sure, because I mean, I could just use 16 bits and it would be like half the size. When am I ever gonna add 24 bits to 24 bits? This just will never happen. In fact, the actual computer itself is gonna just get massive because I just thought of how to do it better. So if we can add 24 bits together, then we need a system that stores all those 24 bits, but we also need a system of our 4 opcodes, which are all 4 bits. So we'll have this is going to be, you know, what we're performing the operations on, but then we're going to have a system that's going to tell it what to do, and it's going to use extra bits. So we're going to end up with like 1,000,000 bits of just storage space out in this direction. If you couldn't tell, I am very excited. Not because of how stupid I've planned this to be. You know, before I did it. But maybe somebody will have a use for adding 24 bits together. And it's not even using a multiple of 4. How can we convert 24 into hex? You can't... I mean, maybe you can. We could actually convert this into base 32. Holy crap. We could have a base 32 display. And... at this point, that's just ridiculous. Well, actually, we could just use the ASCII system to represent the numbers, even though we wouldn't be using the whole thing. It would work. Base 32 would go, because there's 26 letters in the alphabet, and if you, hold on, if you add, is there 26 letters in the alphabet? It's been a while since I graduated kindergarten. I'm thinking it's like 25 or 26, because we got, I'm not gonna sing my ABCs to count, but I'll just go through it in my head. Do. Basically, you need a character to represent every number up to 32 to do base 32. And I think we could definitely make a display that displays base 32 numbers. And I'm not even sure how to do a display panel. So I've been thinking about how to do it, and I was thinking about serial data transfer and all that stuff. I'm gonna go ahead and show you all why it's so complicated to do a display. After we finish this, I need to finish this and stop getting sidetracked, because if I get sidetracked, I'll get on a tangent about how complicated something's about to be. But hey, we're almost done with this. Before we have to do the OR gates, we just need the OR gates, and we need to finish these last XOR gates. And if you're wondering how these work, other people have explained them before, and I have too. But first, let's get these done. Do. I'm just gonna focus and not talk about anything, so I can keep two things in my mind at once. Just for a second. We're gonna talk about the display after this. Let me check and see that I got all of those done. Okay, so now I'm going to talk about what I'm doing while I do it and make it seem kind of simple. So now that we got most of the XOR gates done, we need to add inputs. But we also need to add a piece of redstone dust here, 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 and just keep going down, because this redstone dust is the most important redstone dust that has ever existed. By the way, if you want to see the statistics for this world, this is the most ridiculous part. 40,000 redstone dust, 6,000 repeaters. This is for 2 computers, by the way. That is just ridiculous. The amount of redstone dust. I mean, it would be impossible for one person to build this. Maybe. People have done it before where they build computers, but I don't know that they would build like a massive computer in survival mode. Like, there's only a few people who I could think, or a few groups of people who I could think would use that in survival mode. And computers that really are just like a big specialized logic gate. But seeing as we're getting into opcodes and stuff, we might end up with something that's not just a big logic gate. We might end up with something that can actually do something and can be sentient. And I want to get something that passes the Turing test in Minecraft. That is my goal, is to do the most useless thing ever with a Minecraft computer. Well, it's not the most useless thing ever, but to make the most useless thing a Minecraft computer and make it do something that's also not useful. I can't really find a use for these things. They're just so big. I'm just ranting about that now. But let's be done with rants, and let's get on with important stuff. Repeater here. Put a repeater there. Repeater there. Boom. Boom. Oh, crap, that's a hole. We don't want a repeater there. So basically, these repeaters are going to power this redstone dust. That redstone dust is going to turn off the torch when these are on. But if the top one's on, that redstone dust also gets turned on, and the torch will get turned off, and things will happen. So, it's a bit complicated to explain, but if I showed you it happening, it would make sense. I'm not going to show you it happening, because I don't have to make it make sense. I'm just here to make it do something cool for y'all. So, then after this, we're going to sync the whole system together. And then we have our arithmetic logic unit done. Carry inputs. So, these green ones are OR gates. And they're connected to AND gates and the XOR gates of the next one. So, that is how these things work, kind of. That's just like a tidbit of what they do. Basically, these OR gates, they go across these redstone towers I have set up. And they just carry the number from the previous operation over to this one. And then it allows us to basically carry the number over. Other people have done this, explain these things better than I do, so. Of course, doing redstone, I think it's about making things simple for other people. Because other people struggle with redstone. But I mean, maybe they want to make this at home. Maybe they want to make a redstone computer at home. Maybe they're following along. I have to make sure that these things are slightly understandable. But even then, I don't really care enough to make them understandable. So that will turn on this XOR gate and that AND gate. So that's cool. Turns that one on.